Hi. Today we're looking at gravitational fields and potential energies. So by the end of the day, you will hopefully be able to explain what is meant by a gravitational field and potential energy. Most of these things should be fairly familiar to you. The starter, just reviewing some things. Name 5 different types of energy. And then can you give me 5 equations linked to energy? What is Hooke's law? How do you work out the spring constant? And how would a spring with a high spring constant be different to a spring with a low spring constant? Okay, pause, answer the questions. I'll give you the answers in a moment. Okay, so 5 different types of energy. We can have anything from kinetic, thermal, we can have elastic potential, we can have chemical, and what's that for? We could also have light. Nice and simple. For equations that link to energy, okay, the equation for kinetic energy is half mv squared. The equation for thermal energy, where we're thinking about specific heat capacity, it's E is equal to m shc delta T. Oops, that's a T. Elastic potential energy is half kx squared. That's 3, and a fourth one. Energy is equal to charge times voltage. You could also do power times time. That's 5. What is Hooke's law? Hooke's law, in the simpler form, is just saying F equals kx, or the extension of a spring is proportional to the force applied to that spring. How do you work out the spring constant? There's 2 ways you can work out the spring constant. You can work out the spring constant by rearranging F equals kx, so F over x equals k, or if you've plotted a graph of force against extension and you've got a straight line, if you take the gradient of that straight line, you will get the spring constant. How would a spring constant with a high spring, with a high spring constant be different to a spring with a low spring constant? Okay, so high spring constant. So here we go. If this is high, so if you've got a high spring constant, because spring constant is force, newtons per meter. So how many newtons you get for a meter? So if you've got something that is a high spring constant, that means it's very stiff, whereas something with a very low spring constant, that means it's easier to move. So if you get a low spring constant, this number is small, it means it's very easy to stretch the spring. If it's a big, it's difficult to stretch the spring. Okay, so let's just I'll read this for you. What is a gravitational field? A gravitational field is a region where a mass experiences an attractive force. All mass in my head's in the way. All masses have a gravitational field that causes attraction. You'll need to recall this equation. Gravitational force, N, is equal to mass times gravitational field strength. And you can see here is the Earth. It is a sphere. It's not flat. It really isn't. It is a sphere. When we notice all those arrows are pointing towards the middle of the Earth, because gravitational attraction works towards the center of a large mass. Now, if you can see, these arrows are going in, so they're all kind of at different angles. But as you zoom in close, you notice that those angles become less obvious, because the Earth in the local area, the curve is so gentle, it appears flat, and so the arrows are just pointing straight down. So they're vertically down wherever you are, but they all actually point towards the center of the Earth. So wherever you are, the gravitational attraction due to the Earth is going to pull you down to the middle. I'd note that equation down. The gravitational force, gravity force, is equal to mass, which is in kilograms, multiplied by the gravitational field strength. Done? Splendid. The gravitational field strength, G, or the gravitational constant, G, is a measure of the force on the mass when it is in a gravitational field due to another mass. Mass does not change, but the force on the mass depends on the field. A gravitational field is a region where a mass experiences an attractive force. The same size force acts on each object. The force is bigger if the mass of one of or both of the objects is bigger and the distance between them is smaller. Let's go through that. What does that mean? So G, the gravitational constant, it tells us how big the force of gravity is due to this mass. So for example, if this was Earth and this was me, okay, as heavy as I have got during lockdown, I'm nowhere near as big in mass as the Earth, okay? So the Earth has a gravitational attraction. It pulls me towards it. I also pull the Earth towards myself. But because I am so small relating to the mass of the Earth, the force that the Earth exerts on me is quite substantial. The force I put upon the Earth with its enormous mass is very, very small and minimal. So small, you wouldn't even notice me pulling the Earth towards it myself. The gravitational field is a region where the mass experiences an attractive force. So if I'm near the Earth, I will experience the Earth's gravitational field. If I'm very far away from the Earth, I won't. In fact, as I get further away, the effect is smaller. So as this distance increases, so as I went further and further away, the effect of gravitational attraction of the Earth gets smaller. So actually, if I can get far enough away, I will no longer be gravitationally attracted to the Earth, and I can go off into space and do space stuff. The force of attraction will get bigger. If the Earth got bigger somehow, then I would be pulled towards the Earth with a greater force. If the Earth got smaller, I would get pulled towards the Earth with a smaller force. But the Earth's not going to get bigger, and the Earth's not going to get smaller. But what are bigger and or smaller are other planets. Now, weight is one of those things that we use perhaps the wrong term in everyday language. When people talk about them getting their weight, they step on the scales, they might do it in kilograms or stones and pound, but that's not their weight. That's actually their mass. Now, your mass is like what you're made up from the little bits, whereas weight is actually a force. And it's a force on Earth due to you being on Earth. So the Earth pulls you, and the force that it pulls you towards you is your weight. And you can work that out using this equation. It is mass multiplied by the gravitational field strength. So your weight, W, is equal to mass times the gravitational field strength. You can work that out using a scale. So if you get on the scales, get your mass in kilograms. So if you're me, quite a lot, 90 kilograms. And then you multiply it by the gravitational field strength. On Earth, it's a nice, handy 10. So my mass is 90 kilos times by the gravitational field strength of 10. So my weight is 900 newtons. 900 newtons. So on the surface of the Earth, G is 10 newtons per kilogram. The value of G depends on the mass of the Earth and the radius of the Earth. The weight is also what we call the gravity force on planets and moons. So if your weight on Earth was 100 newtons, that's very small. What would be 100 newtons? A cat, okay? If you weigh 100 newtons on Earth, how would it be different if you went to different planets? So, for example, here is the moon. Because the moon is much smaller than the Earth, and more importantly, it's much less massive. Its mass is less. If you weighed 100 newtons on Earth, you'd only weigh 16.6 newtons on the moon, which is a very, very small amount. Very, very small. If you look at Venus, Venus not too different to Earth. If you weigh 100 on Earth, you'd weigh 90 on Venus. You would feel lighter, but it's not massively different. Let's look at something more dramatic. Jupiter. Jupiter is enormous and incredibly heavy. And so if you weighed 100 on Earth, you would weigh 236 on Jupiter. over twice as heavy as you would on Earth. Saturn is a weird one. Saturn's really big, like Jupiter, but Saturn is really light. It's very low density. In fact, Saturn is such a low density. If you could find a big enough ocean, it would float. So if you weighed 100 on Earth, you'd only weigh 106 on Saturn. So that's pretty similar. If you were to go to the sun, which you can't, because the surface is about 7,000 or 8,000 degrees and the core is about 150 million degrees, you wouldn't weigh 100. You'd weigh 2,707 newtons, which is a lot. So ignoring the fact that the heat and the radiation would kill you, the force of attraction would crush you thinner than a pancake. Is there anything to write down from this? Make sure you have the equation for weight. Weight is equal to mass times gravitational field strength. And on Earth, it's 10. Okay, let's have an example or a question. Question, the object is a 10 kilogram kettlebell. I notice actually on the print it says 16, but I've done it 10 to make it simple. The force needed to lift an object equals the object's weight. Calculate the weight of the object lifted. Write unit with your answer. So basically, what's the weight of this 10 kilogram kettlebell? Remember, weight is a force. It's not the same as mass. Calculate the work done in lifting the object. Use an equation. I haven't put a number in. Lifting the object, we'll say 2 meters. Lifting it above your head. You're doing your exercises and you're lifting the bell above your head. Lifting the object 2 meters. Use the equation work done equals force times distance moved. And then when you lift the object, what energy store has increased? Where has the energy gone? Because it was perhaps in your chemical energy in your muscles and you've lifted it. Where has it gone to? Pause answer. The answers will come in the next lesson. So what is acceleration due to gravity? So we talked about this before. If you're on Earth, gravity will pull you towards it. Notice, gravity isn't the force. Gravity causes the force, which is your weight. If you're ever asked to do a diagram and the arrow asks to draw the force and you write gravity, that's wrong. Gravity isn't the force. You can say the gravitational force, due to gravity, okay, the gravity force, but it's the gravity itself isn't the right answer. If you just wrote gravity, that would be incorrect. So it is, obviously, the force is F equals ma. Mass times the gravitational field strength, which is the same as mass times the acceleration. So on Earth, as we have said, the gravitational field strength is 10 newtons per kilogram, but it's also 10 meters per second squared. More precisely, if you carried on doing physics at A level, it would be 9.81. So when you lift an object in a gravitational field, you transfer energy to its gravitational potential store. This is called gravitational potential energy. The equation for this, gravitational potential energy, should have done this in blue, is equal to mass times height times gravitational field energy. Gravitational field, hang on, that's wrong. Gravitational field strength, that word energy, something's gone wrong with the formatting. Gravitational potential G equals mass times height times gravitational field strength. Sorry, something's gone wrong when I've copied and pasted from something else. Shame on me. Okay, so let's do an example of a question. Where gravitational field strength or gravitational acceleration on Earth is used in a calculation, the value of 10 should be used. Show you're working and write the units. Calculate the increase in gravitational potential energy when a book of mass 0.5 kilos is lifted from the floor to a shelf 2 meters above. So gravitational potential energy, GPE, is equal to mass times height times gravity, gravitational field strength. So 0.5 times 2 times 10. It's like they've chosen those numbers specifically. 2 times 10 is 20, times half is 10. And that is joules. Say the work done when a person lifts a book of mass 0.5 kilos from the floor to a shelf. Okay, so the work done is equal to force times distance. The force, well, to turn that into a force, we need to do 0.5 times 10. And the distance is 2 meters. 0.5 times 10 is 5, times 2 is 10. So, note, those are the same thing. The gravitational potential energy is the same as the work done when you're going vertically. The gravitational potential energy is the same as the work done when you're moving vertically. And now it is time for you to do some more questions. During their migration, monarch butterflies have been seen by glider pilots at altitudes of 1,200 meters. The mass of a monarch butterfly is 0.50 grams, and the mass of a glider pilot plus its pilot is 450 kilograms. Calculate the change in gravitational potential energy of the glider plus pilot when it goes from the ground to 1,200 meters. I just did the example before. Then convert the mass of the butterfly from grams into kilograms. Be careful, because it's 0.5 grams, not 0.5 kilograms. And then calculate the change in gravitational potential energy of the butterfly when it flies from the ground all the way to 1,200 meters. Pause, answer those questions. Done? Splendid. Ooh, quite animal friendly today. Bar-headed geese fly over the Himalayas when they migrate. They have been observed to gain 6,000 meters in height during a period of 8 hours. Calculate the gain in change in gravitational potential energy when one of these geese has a mass of 2.8 kilogram, gains 6,000 meters in height. Wow. What energy is required to lift a 2.8 kilo goose to a height of 6,000 meters? Note, it's on Earth, so the gravitational field strength is 10. Use your physics knowledge to suggest why birds usually avoid flying this high if possible. That's tricky, but think about it. Calculate the average power. Remember, power, P, is equal to energy over time. Okay? You've worked out the energy to get you there. Work out, and then do it for 8 hours. Remember, time must be in seconds. The bar-headed geese fly at speeds of 30 meters per second, 67 miles an hour. Wow. You got hit by a goose, you'd be in a bad way. Calculate the kinetic energy of a goose flying at this speed. Remember, kinetic energy equation, we did it in the starter, shouldn't be too much of an issue for you. A ball of mass 0.2 kilos is dropped from a height 5 meters above the ground. Calculate its speed before it hits the ground. Ooh, this one. Okay, so you can use this and the number 10 to work out its GPE. Once you've worked out its GPE, you know that when it starts here and then goes, when it's on the ground, GPE equals 0. Your gravitational potential energy is 0 when you're on the ground. So that gravitational energy kind of just disappeared. It's turned into kinetic energy. So KE will equal whatever that GPE was earlier. Then you have to do that clever rearranging when you work out the velocity. That was a couple of lessons back. So, multi-stage question. Work out the GPE, put that equal to KE, rearrange, change the subject, change the subject for velocity. And that's it. Okay. I'll give you the answers to tomorrow in tomorrow's lesson. Try your hardest. I know you can do it. I believe in you. Love you. Bye.